free particle. Free particle means particle is free, there is no potential, and we should solve again Schrodinger equation. We shall see what would happen. Okay, what does our Schrodinger equation gives and what are the interpretations. Minus h bar square by 2m d square psi by dx square is equal to E into psi. There is no V part. Okay, V equal to 0. Free particle means potential is equal to 0 everywhere. Potential equal to 0 everywhere. Yeah, any problem? Yeah, is there any problem? Any problem with the video? Yeah. If I rewrite this one, d square psi by dx square is equal to minus 2m e by h bar square psi d square psi by dx square plus 2m e by h bar square psi is equal to 0. Is that okay? Now again, as our old what you call idea, what we take this one as some square of some other quantity, so that differential equation can be solved very comfortably. Is equal to 0. Okay, where k is equal to root of 2m e by h bar. When you solve this equation, psi of x is equal to, because auxiliary equation solution is plus or minus I into k. Am I right? D square plus k square equal to 0, plus or minus I into k. You can write it like this: a e power I kx plus b e power minus I kx. b e power minus I kx. Is that okay? That's the solution. I prefer writing in exponential, not in terms of sine or cosine. Okay? Because it will represent plane wave, just similar to our electromagnetic wave. It will represent plane wave. We shall see that one. And we prefer writing in exponential because it's easy to handle mathematically. Exponentials are easy to handle. Okay. Now look at here. If I write my psi of x comma t, isn't it? If I write my psi x comma t, again obviously, what is my energy here? How do you define energy out of this one? Energy is equal to h bar square k square by 2m. Can I write like this? If you solve it for energy, h bar square k square by 2m. Okay. So that's equal to psi of x into e power minus I e t by h bar. Okay. Now let me plug in the time dependent part. Let me see what is this one. What is the what kind of function it is. Is that okay? Now you got only time independent part here. Is that okay? Now when I plug in that one, look at here. If I multiply with this one, let me write the resultant wave function, that's equal to a e power I. Let me take a k outside, x minus h bar square k by 2m into t. No, h bar k by 2m into t, because e t by h bar and k is taken outside. If you multiply inside, h bar k square by 2m. Okay, e t by h bar, e by h bar, and k, one more k is taken outside. Is that okay? Plus again, try to do this one again. b e power minus I k. If I take minus I k outside, you will get x plus h bar k by 2m into t. h bar k by 2m into t. Is that okay? H bar k by 2m into t. Now look at this one carefully. This is a function of x minus vt. This is a function of x plus vt. This will represent traveling wave. I'll discuss later, I mean in electrodynamics, how this kind of function will represent wave which is traveling from one position to other position by carrying energy in case of electromagnetic chapter. Is that okay? But now you should believe that this will represent a kind of traveling wave. Again, this part will represent wave traveling to the right, x minus vt. This kind of function will represent wave traveling to positive x-axis. This kind of function, okay, function of x plus vt, that's it. Okay, you can take either plus minus whatever, it doesn't matter. Here also you can take plus minus outside, that doesn't matter. This functionality does matter. This will represent wave traveling to the left, negative x-axis. Okay, again those are combined. Now what we do here is we want to merge these two. We wish to write. Again, you can call this one as a matter wave, but look at it, there is a lot of problem with this one. Okay, a lot of problem with this expression. Again, before interpreting, we shall get into that. Okay, wait a second. Now again, one is wave traveling to the right, other is wave traveling to the left, isn't it? This part is wave traveling to the right, positive x-axis. This part is wave traveling to the left. Now we wish to merge these two and we want to write only one expression. While merging those two, what we do is, we haven't taken any sign for k, isn't it? Now we will put sign for k. If k is positive, it is wave traveling to the right. If k is negative, it is wave traveling to the left. We wish to write the expression like that, merging these two. Because both of them are, it will represent one, it will represent other part. Suppose if you take only wave traveling to the right, then you should avoid this one. Suppose if you are talking about wave traveling to the left, again you should avoid this one, isn't it? So that's why I'm talking about one of the situations. So that's why what I do is I'm going to merge these two terms and I'm going to write it like this: a e power I kx minus h bar k square by 2m into t. Okay, let me write my psi of x comma t like this. Okay, now you can ask the question how this will represent both wave traveling to the right as well as left. Okay, suppose if k is positive, if k is positive, this will be of the function of x minus vt. If k is positive, is that okay? Then again psi of x comma t is of the order of f of x minus vt. If k is negative, what will happen? One negative sign, one more negative sign. You can take that negative sign outside. That will be form of x plus vt, function of x plus vt. Is that okay? So so write down again. If k is less than 0, your psi of x comma t will be of the form f of x plus vt. If k is negative, this is also negative. Take that negative sign outside. Okay. It doesn't matter what is the sign outside, it does matter what kind of function it is. Is that okay? It is of the form x plus vt. So that's why if k is greater than 0, it will represent wave traveling to the right. If k is less than 0, it will represent wave traveling to the left. We can write only one expression where psi, which depends on k, can I write like this? Psi of k, just like psi n we write earlier. So my solution is psi k x comma t, that's equal to a e power I kx minus h bar k square by 2m, not h bar square. Okay, divide by h bar was there in the energy expression, be careful. Kx minus h bar k square by 2m into t. K is greater than 0 for wave traveling to the right, k is less than 0 for wave traveling to the left. Only one expression can represent both cases. No, small v means this is the velocity of the wave. Okay, I'll talk about that one. If you write your wave equation in terms of wave function in terms of x minus vt, suppose if you talk about electromagnetic wave, where v is the velocity of the wave, we call it as phase velocity. Again, you need some more ideas over there. Let me talk about that one. Okay, we call it as phase velocity, x minus vt. V is the velocity of the wave. Let me talk about that one. Now, when I see this one, look at here, when I see this whole thing, what is my, what is my velocity, speed of the wave? Again, that's what he talked about. Again, this capital V is potential, okay? It was potential. It was velocity. Don't get confusion. Now look at here. What I was talking about here is, velocity, am I right? Suppose if you take k outside, that's equal to, if you take k outside, e power I, k outside, x minus h bar k by 2m into t. If you compare this one with function of x minus v into t, what is v here? H bar k by 2m. Isn't it? In place of v, you x minus vt. So that's why velocity of the wave, speed of the wave, okay? Speed of the wave, the speed of these waves you can imagine like a matter wave, but I'm not going to interpret like this. Yeah, definitely we can represent this one as a linear combination. Okay, that's a very good question. Again, we will not be able to express our solution as a linear combination of left and right. We can do that one. Now we can, again, it was a kind of linear combination only. Okay, it was a kind of linear combination only for two different solutions. This one was individually solution, this one was individually solution, linear combination is also solution. But I prefer writing one equation where I'm restricting myself to either traveling to the right or traveling to the left, not superposition of them. Okay, we have other problem, interpretation problem, we shall see. Speed of these waves, you can take k outside, you can grab that term, that's equal to, he calls that as v quantum. Okay, v quantum, v quantum, that's equal to h bar k by 2m. Is that okay? Now if you write E is equal to h bar square k square by 2m, what I write is, I'm going to write as p square by 2m, scalar. I'm not putting cap here. Okay, I'm not putting cap here, where I'm going to express p as h bar into k. Is that okay? Another expression, E is related to k like this, that's equal to, I'm going to write as scalar p, not operator, it's not Hamiltonian. Okay, p square by 2m, where I represent p equal to h bar into k. Now I wish to write this whole thing in terms of E actually. So what I can write is, I can write this as root of, what is h bar k? Root of E by 2m, E into 2m, what is this one? H bar k by 2m, how do I write? Into 2m divided by 2m, is that okay? Divided by 2m, I can take root, this 2m, I will take it here, I can write this one as a root of E by 2m. Velocity of the, speed of the wave. Okay, we can write like this. So, but what is speed of the particle? What is speed of the particle? Okay, again he calls that one as v quantum. Okay, v classical speed of the particle. What is this one? I can write this one as momentum by mass, simply speed of the particle, isn't it? Non-relativistic, okay? You don't have to worry about relativity here. A particle moving with non-relativistic speed. You can write this one as P by m. How do you write P by m? I think root of 2e by m. Just check it out. You can write in terms of actually P equal to root of 2m into e divided by m. Is that okay? P is equal to root of 2m into e. Or I again, if you prefer, you can write like this: h bar k by m, or P by m, momentum by mass, or h bar k by m. That can be written as again using this expression, the root of 2e by m. And you got one expression. Look at here. This is double of this one. Wave function is a kind of traveling wave. Is that okay? And it will move with speed this one, but particle is moving with a speed double of this one. Look at here. Is that okay? Again, he writes one sentence. Let me just give you the sentence. Quantum mechanical wave function travels half the speed. Quantum mechanical wave function travels half the speed. This speed is half of this one. Half the speed of the particle that it's supposed to represent. This is representing this free particle. Am I right? That free particle is moving with this speed, but our wave function is traveling with half of that speed. Is that okay? We can write v quantum, that's equal to half of v classical. Any question quickly? Just one observation, okay? We shall talk about this one. I should talk about dispersion and all. That's a different story. Again, I should talk about phase velocity, group velocity and all. Let me take it, so take those things in the next class actually. Now look at here. So, is that over? While solving Schrodinger equation, in case of particle in a box, in case of harmonic oscillator, we got one restriction to energy, isn't it? We got one restriction to energy. Now we haven't got any restriction to energy in case of free particle. Energy can be any value. Is that okay? Energy, we define that one as h bar square k square by 2m. Am I right? We define our Schrodinger equation like this: d square psi by dx square plus k square psi is equal to 0, isn't it? We convert it into this format, and then we define energy like this, and nowhere we got any restriction to energy. Energy can be anything here. It can be 0 also, isn't it? There is no restriction here, isn't it, on energy. But one thing you should observe, again, there is no restriction on k also, isn't it? So k, again, earlier in case of particle in a box, you have written the similar equation, isn't it? But you got some restriction for k by applying boundary condition of 1D box. But there is no condition here, it is free everywhere. That's why k can be any value, energy can be any value. Is that okay? As well as again, momentum, we can define it as h bar into k. It can be any value, okay? Wait a second, there is a problem with this solution. Let me talk about that velocity later, okay? Again, I need to talk about group velocity and phase velocity. Yeah, wave function velocity is half of the velocity of the particle. We shall discuss that one, okay? Because this kind of thing will not happen. Let me argue. Now, my next argument is particle cannot be in this state. Let me tell you what is the problem. Now look at here. This is the state with very known k, isn't it? That means this is the state with definite momentum, as well as this is a state with definite energy. I mean, if you know k value, means that k value will decide energy. This is a state of definite energy, as well as this is a state of definite momentum. The problem is it's a state of definite momentum. Uncertainty will not allow us to have such a state actually. If this is the state of definite momentum, what would be the uncertainty in the position? That will be infinity. That okay? If you find sigma p here, okay, find sigma p in this situation. Find sigma p. What is this one? Root of whole square. Is that okay? Now look at it. Let me operate p cap on this one. I said this is a definite state of momentum. Am I right? Definite state means you know what exactly its momentum is. Is that okay? Because k will decide momentum. I have written the expression. Okay. Let me operate p cap on this psi of k. So just check it out. What would happen if you operate minus I h bar dou by dou x into a into exponential of whatever minus I h bar. When you take derivative with respect to x, I k will come outside. Into again same wave function will happen. That's why if you operate momentum operator on this psi k, what you get is minus I square, that's equal to plus 1 h bar k into psi k. Whatever state we have, that is the eigenvalue equation. Operator, function, constant function. What is the state we have? That is the eigenstate of momentum operator. Eigenstates are definite states. If it is eigenstate of momentum operator means I know in this state what is the value of the momentum accurately. Once it is an eigenstate, look at here, you can find expectation p cap square p square. Actually, you can't do this one. Because to find expectation value, it should be normalizable. The function is not normalizable. That is the next argument. It's a definite momentum state. That is the one of the observation you can do. Okay, just observe this one. This is the eigenstate of momentum operator. Earlier we talked about energy eigenstates. Am I right? Energy eigenstates are eigenstates of Hamiltonian operator. Now this is an eigenstate of momentum operator also, along with eigenstate of Hamiltonian. It's an eigenstate of momentum operator also. Okay. Yeah, I'll come to the point of velocity later, okay? Because again, even though it looks like it will travel with half the speed and all, but this kind of state is not possible. First, we should look into that one. Now look at here. Try to normalize this one. What is the range here? Minus infinity to plus infinity. Particle can be anywhere, isn't it? So then, if you try to normalize mod a square minus infinity to plus infinity, what is this one? Mod square of this one, e power plus e power minus e power 0, that's equal to 1 dx, isn't it? It diverges. It is not square integrable at all. When you take mod square, you will get mod a square. Integration of minus infinity to plus infinity 1 dx. Don't write anything, okay? That's 10 to infinity. Okay, I hope you know that one. So that's why it is not square integrable. It is not normalizable. If it is not normalizable, we say it is not physically acceptable. Because if it is not normalizable, then we can't do any interpretation. We can't do any probabilistic interpretation. We can't take any expectation value using this one. Is that okay? The wave function is not normalizable. And we say non-normalizable solutions are not physically acceptable. So that's why we interpret that there is no state like this. There is no state which has a definite momentum. There is no state which has a definite energy. This is a state of definite energy. There is no free particle with definite energy. Can you write one sentence? Function is not normalizable. Hence not physically acceptable, or hence physically unacceptable. Wave function is not normalizable and hence physically unacceptable. No, again here, energy is positive only. Again, what is the potential equal to 0? What is the minimum value of the potential? 0 only. Energy is greater than 0. I am talking about energy greater than 0 only. Is that okay? But even though energy is greater than 0, for a free particle, it turns out that solution of the Schrodinger equation which is not normalizable. Hence, it is not, again, physically unacceptable. Is that okay? It is physically unacceptable. If it is not normalizable, we can't do any probabilistic interpretation. We can't find any average values. Is that okay? Now, what do you mean by that one? Physically, there exists no state like this. This is the state of definite energy. Look at here. If I operate h cap on this psi, okay, what you get is you get E into psi. E is nothing but h bar square k square by 2m. If you operate p cap on psi, another observation. That's why I write psi k actually. Okay, you get h bar k into psi. This was definite momentum as well as energy state actually. Okay, it's a state of definite energy. Now this kind of state is not, again, we solved this equation and we found that one. Is that okay? We solved Schrodinger equation actually. So we say that kind of state is not possible. Particle cannot have definite energy state, or particle cannot have definite momentum state. Free particle, I'm talking about free particle, okay? We had definite energy state for particle in a box, or stationary states have definite energy state. In case of harmonic oscillator, it was possible, but for free particle, there is no free particle with definite energy or momentum state. Is that okay? Can you write down that sentence? There is no such thing as a free particle with a definite energy, or in bracket write momentum. Yeah, wait a second, let me answer those questions. There is no free particle. There is no such thing as a free particle with a definite energy, in bracket write momentum, because momentum will decide energy, E equal to p square by 2m. Okay. Now his question is, in free particle case, we're discussing with a constant velocity. Am I right? It's a conservative system. Okay, energy is equal to constant. If it starts with the velocity v, its velocity will not change if there is no potential. Again, Newton's law, isn't it? Again, if it starts with uniform velocity, if there is no force, it will continue with that one. Is that okay? It's a constant energy situation. Is that okay? If there is no potential, velocity will not change. If it starts with some initial velocity, it will continue with that motion actually. Okay. Again, if potential equal to 0, velocity will not change. Okay. So that's why we are talking about situation of potential equal to 0, that means force equal to 0. There is no question of change of velocity. If you start with one velocity, it will continue with that velocity. Not like that. Okay, if particle have got definite energy, it need not to have definite momentum. Suppose if I take psi n of x is equal to root of 2 by a sine n phi x by a. Okay. If you operate h cap on this psi n, what you get? You get En into psi n. This is a definite energy state. Operate p cap on this one. You will not get any constant into psi n. That's not definite momentum state. Is that okay? That was definite energy state. Particle in a box problem. Is that okay? That's a good question. If particle has definite energy, is it necessary that it should have definite momentum? No, it need not to have definite momentum. Is that okay? You had, for this state, nth stationary state, you found sigma p x, am I right? What do you mean by uncertainty in p? That means distribution. If you do the measurement, you are getting different momentum. Is that okay? You had a standard deviation in the measurement of p. That means it is again, this is non-zero. Am I right? This quantity was non-zero, so that's why it is not state of definite momentum, but it's a state of definite energy. Again, for this state, we found sigma e or sigma h. Am I right? That was 0. Standard deviation in the measurement of energy, that was 0. Observe those facts, okay, mathematically. Yeah, these are not state of definite momentum, 1D box or whatever, because if you take derivative, you will get some other function. Once you take derivative, you get cos function. You cannot write that one as constant time the same function. They are not eigenstate of momentum, okay? No, that doesn't mean we can't have a wave function. We can't have a state with a definite momentum or energy for a free particle. We can have definite energy state for a particle in a box, harmonic oscillator. Okay. Now we should fix the issue. What is the issue? We can't have what you call free particle with definite energy. Then what is the use of this solution? But this is a solution of Schrodinger equation, remember. Even though it is physically unacceptable, but this is a solution. Now how do we make use of this one? Now what is the use of this one? Wait a second, I got a couple of questions. Definite energy states are forbidden for free particle because again it is not normalizable. Okay, that is the main story. Main problem with this solution is it is not normalizable. That's why it is physically unacceptable. And you can give another interpretation. This is a definite momentum state also. If it becomes definite momentum state, position uncertainty will become infinity. Both of things you can interpret like that. Particle cannot be in any stationary state. That's correct. Okay. Free particle cannot be in any stationary state. Stationary state means definite energy state. Okay. That's correct. That's correct interpretation. Okay. Yeah, if function does not vanish at x tends to plus infinity or minus infinity, that does mean that particle can go to infinity. Again, if particle goes to infinity, particle can vanish, isn't it? Again, physically unacceptable. Those things are physically unacceptable. It doesn't vanish at plus infinity or minus infinity. That causes a non-normalizability. It is non-normalizable because of that fact. Again, where does momentum is changing? Momentum is not changing. Okay, I'm fixing one of the k value and I'm thinking over it. Okay, I'm taking one energy. I'm talking about one momentum. I'm talking about one k value, state with one possible k value. I'm talking about that. Is that okay? It's not any function or something. No, again, we are talking about, don't think like that this is the situation of E less than V minimum. I'm not talking about this one. E is greater than V minimum only. Okay, we are not talking about that theorem, isn't it? We got non-normalizable solution if E less than V minimum. All right, I'm not talking about that one. We are in the regime E greater than V minimum only. Even though E greater than V minimum, if you solve Schrodinger equation, is that okay? Actually, there is a two distinct thing. One is bound state, other one is scattering state. This is a scattering state problem. Let me discuss in the next chapter. That theorem, we better to apply that theorem only for bound state problem. Whatever the theorem you talked about, if E less than V minimum, it is not normalizable. We better apply only for bound state. This here you can't apply that one. E greater than V minimum only. So what that theorem says is, look at it, he was very careful while defining that theorem. Wave function is not normalizable if E is less than V minimum, isn't it? If E is greater than V minimum, only in case of bound state problem it is normalizable. Is that okay? In this case it is not. Don't think of that situation, okay? That theorem right now. Let me clarify that one later, okay? Let me take that theorem later. That's only for bound state actually. Yeah, definitely. These are propagation waves actually. This is a kind of, again, even if you solve Maxwell equations, again, you can solve Maxwell, you can form a wave equation out of Maxwell equation. If you solve it, you will get this kind of answer, electromagnetic wave, okay? Those are stationary states, they are propagating waves, definitely. Free particle cannot have definite momentum. If a free particle have got definite momentum, then again we got problem with uncertainty. Again, this also definite momentum state, it is not normalizable, okay? Definite momentum state or definite energy state for a free particle is not normalizable, physically unacceptable. Okay, yeah, I just rubbed out that one. Psi k x comma t, that's equal to e power I kx minus, what is this one? H bar k square by 2m into t. Now look at here, since there is no restriction on k. Earlier I had written psi of n, isn't it? Because my answer my wave function was depending on an integer n, isn't it? Now this depends on k, that's why I write k here, but there is no quantization restrictions here. There is no quantization here, okay? Now look at here, what is the use of this one? The next question is, if we can't normalize, if this is not physically unacceptable, but still this is a solution of Schrodinger equation. But Schrodinger equation allows one more property. If you linearly combine solutions, that's also solution, isn't it? How to linearly combine them? Earlier we combined, look at here, if psi n of x, if this was the solution, am I right? Again, what we have written, general solution, we have written as Cn into psi n, am I right? Remember, this summation was summation over different state of different energy. Psi n means those are states of energy eigenstate, that's what we said, am I right? You took summation over different n means you took summation over different energy value, energy eigenstates. Now similarly, if I want to do that kind of linear combination here, but here you had quantized energy states, am I right? E1, E2, E3. That's why you had a summation, but here you have continuous energy. Is that okay? Now look at here. Now rather than talking about energy, I'll talk about K, or I can talk about momentum, because K will decide energy, am I right? E is equal to h bar square K square by 2m. K will decide energy. That's why I can say this has state again. This have got where K is continuous variable here, but here in case of particle in a box, energy was not continuous variable; it was discrete. You made summation over n. That means you made summation over different energy states. Now I need to make summation over again energy, different energy state. I mean I need to linearly combine so states of different energy that is equivalent to linearly combine states of different K. Can I say like this? But K is continuous now. So that's why that summation will be replaced by integration here. Is that okay? Now the thing that I'm going to write, look at here. I'm not writing summation, but this exactly similar to that one. Since we had discrete energy, we had a summation here, discrete wave function. Again, since we have a continuous energy, continuous K, we have integration here. We will not integrate with respect to energy. We can do like that also, but we avoid that one. We integrate with respect to K. This is just similar to that one. This is similar to linearly combining them. And Schrodinger equation will allow that this is also solution, whatever I'm writing. Why? Linear combination is also solution. Linear differential equation property. Okay? Integration of, what we write is integration of e power I kx minus h bar k square by 2m into t. Okay? Again, I'll come back to this situation. You had a coefficient which was Cn, am I right? Which depends on n. N will decide energy. En is equal to n square h bar square by 2ma square, isn't it? Psi n is equal to root of 2 by a sine n pi x by a. Here n will decide energy. Okay, that's why we have written that index n here, isn't it? And this Cn, which depends on n, again n is related to energy again, isn't it? So that's why in this integral, I have to integrate now because I don't have discrete states here, I have continuous state. In that integration, definitely I should integrate with respect to dk, different k value, because here I did the summation with respect to different n value, kind of different energy only. Here also, is that okay? So that's why I should make the summation of different k, but k is continuous here, that's why it should be integration. Now you should have a coefficient which depends on n, so here I should have a coefficient which should depends on k. You are making summation with respect to n here, and your coefficient depends on n, isn't it? And you are making integration with respect to k. Summation is converted into integration here. Your coefficient should depend on k. I call that one as pi of k. Each and every step have got physical ground here. And we put one more factor, 1 by root 2 phi, matter of convenience. Is that okay? Minus infinity to plus infinity. This is most general solution. I write psi of x comma t. This is psi k of x comma t. This is a definite momentum state, definite energy state. This is linear combination state, just similar to this one. Can you find the similarity? In place of psi n, you have this one. In place of Cn, you have this one. You are making summation over n, you are making integration over k. That is the only difference. And don't worry, actually here Cn had no dimension, okay? Cn has no dimension. Mod Cn square was probability, isn't it? Wave function here. But here you have dk, okay? This have got some dimension, this coefficient. Energy is continuous here. Energy is continuous here. There is no discrete energy for a free particle. Yeah, that's correct. What he's saying is, we can check whether it is a definite momentum state or not. If it is definite momentum state, it is not physically realizable. Definite momentum state. If it is definite momentum state, its position will be uncertain. Let me talk about that one, uncertainty. That's a good idea. Now, this is kind of linear combination of this one, and Schrodinger equation allows that this is also solution. Is that okay? Schrodinger equation says that linear combination is also solution. Is that okay? Now, if I take x equal to 0, now this is normalizable. This kind of state is normalizable. This was a solution which was not normalizable, physically unacceptable. But linear combination, it was also solution of the Schrodinger equation, but this kind of state is normalizable. But look at here, this state contains different momentum. This state contains different energy. Isn't it? Just like in case of linear combination state, we linearly combine different energy states, am I right? Suppose C1 psi1 into C2 psi2. Which energy state it has? We don't know. It's a combination, isn't it? It's a linear combination. Similarly, this is not definite energy state. This is not definite momentum state. It is a linear combination of those. So that's why this kind of state is allowed. How do you physically interpret? This state is because of different momentum, which is linearly combined. This state is because of different energy, which is linearly combined. Suppose if you do measurement, you may get one of the energy or one of the momentum, but you don't have definite energy or momentum state actually. Is that okay? This state is normalizable. It is normalizable. One D box does not have definite momentum state. I think you joined late. 1D box doesn't have definite momentum state, only definite energy state. I am taking analogy, okay? I am taking analogy. We make summation over n where n decide energy. We make summation of integration over k where k will decide energy. I put psi n here. This is normalizable solution. Okay, I don't have any integer restriction here. That's why I put k. Isn't it? But this is not normalizable. This is not acceptable. Particle can be in this state. Particle can be in this state also, linear combination state. But free particle cannot be in this state. Free particle can be in this state. Why? This is normalizable. Is that okay? This wave function is not physically realizable, but this wave function can be. But this state have got range of momentum, range of energy, not single energy or single momentum. Okay. Now what I do is I am going to write psi of x comma 0 If I write that on 1 by root 2 phi, 1 by root 2 phi integral minus infinity to plus infinity pi of k into e power I kx dk. This is nothing but Fourier transform. Fourier transform of pi of k. You got the definition now? Fourier transform of pi of k actually. Or you can say psi of x is Fourier transform of phi. Now look at here. Now I'll use my mathematical theorem to write pi of k. What is my pi of k? It's equal to again 1 by root 2 phi. If 1 by root 2 phi comes, one more 1 by root 2 phi should be here. Integral minus infinity to plus infinity psi of x comma 0. This one should come here. E power minus I kx into dx. Using Fourier theorem or Fourier transform mathematical idea. Can I write like this? Where pi of k is equal to this one. So this is just similar to finding Cn. Cn was equal to I think psi n star into this psi. Am I right? Dx. That's what you found. This is similar to that one, but it is mathematically Fourier transform. They are Fourier transform of each other. I better to say like that. I better not to say which is Fourier transform, which is inverse transform like that. I better say one is Fourier transform of other. And we call this one as momentum space wave function. Let me try to interpret that one. Okay, this is nothing but momentum space wave function which has got as much information as that of position space wave function. Again, whatever we are doing the interpretation on that position space wave function, we can do similar interpretation on that momentum space wave function. Both are equivalent actually. Now go through Jatili and try to write this one in terms of P. Okay, in Jatili he writes this whole thing in terms of P. Okay, P is equal to h bar into k. I think one more root of 2 by 2 pi h bar will come here. Okay, he tries to write that one in terms of P. Pi of p e power I px by h bar like that. He prefer writing like that. Okay, go to Jatili and have a note on that. I think we better to discuss. Let me discuss. Try to do example number 2.6 before in example number 2.6. Okay, that's nothing but Fourier analysis. And problem number 2.20. Problem number 2.20. Example number 2.6 and problem number 2.20. Okay, try to do them. Yeah, this 1 divided by root 5 is a matter of convenience. Okay, if you are not taking 1 by root 5 here, you should take 1 by 2 pi here. It's a definition. Okay, it's all left to us. It is all left to us actually. You can absorb this 1 by root 2 phi inside that phi of k. Why not? Then 1 by 2 phi will come here. It's all matter of convenience. 1 by root 2 phi. There is no physical significance. Is that okay? Matter of convenience. And I think, we need to solve some Jatili problem after next session. Okay? We need to solve some Jatili problem because Griffiths haven't mentioned much problem on group velocity and phase velocity. Now comes the concept of group velocity and phase velocity here, and we should solve some problem on that one. Again, Jatili mentioned couple of problems again which appeared in exam also. Is that okay? Yeah.